So today we have Stoudenmire, who will tell us about revisiting the classics, turning old ideas into new methods with tensor networks.
Thanks a lot, Juan. Thanks so much for being here today. I know you guys have a lot of stuff going on and a lot of talks, and so thanks for taking the time. My name's Miles, and I just work your neighbor to the north up the road at the Flatiron Institute. I wanted to take one slide just to say, a bit about who we are in case you've only heard maybe a little bit about us or you've never heard of us. So like how many of you have been to the Simons Foundation before or know about the Simons Foundation? Great. So we're just like across the street. That's our building, and that's the Flatiron building. So we're like one block down. So it's called the Flatiron neighborhood. And we're an interesting place because it's very interdisciplinary. You can see our centers here, our current centers on the slide. We have quantum physics is just a small part, right? So we're like up in the attic a bit, but then down in the foundation, you have mathematics on the bottom floors holding up everything else, right? And then we have a biology and astronomy across the street. We have neuroscience. There's even a new center initiative for computational catalysis. We're hiring quantum chemists to work on sort of cutting edge problems in catalysis using quantum chemistry techniques. So just mentioning a bit about who we are. So we have a big initiative to push numerical methods. And so in a way, this talk is kind of going to be like my love letter to sort of numerical algorithms and methods, just a little bit of an extracurricular topic maybe. So here's the quick 3-slide overview of the talk. So the motivation of the talk is that as many of you know and has been well advertised, there's a lot of very hard problems in the world. There's many problems that classical computers struggle to solve. And I would argue that very many of them relate to the existence of high dimensionality in some way. And so one point of the talk is going to be that we all would appreciate that is the case for, many-body classical and quantum physics, right? Statistical mechanics, famously, 3-body problem, classical, and of course, quantum many-body physics. But another point from the talk will be that there's a nice mapping. I mean, many of you know this mapping, but it's just to emphasize that there's a nice mapping from the many-body problem to the continuous variable problem too, which is kind of a problem. I mean, it's long been known you can fit continuous functions by polynomials if they're smooth, but it's a lot more challenging to fit functions that have discontinuities and fractal structure and lots of other things. So these problems are essentially the same problem mathematically in a certain sense, and I'll show you exactly what that means. And then that's just talking about, spaces and representations and sort of the big picture. Zooming in a little bit, I'm just going to review 2 what you could call kind of classic, I just mean old proposals for working for algorithms to tackle high dimensional problems. And by now, maybe it's in the realm of the classics, maybe that's a little too recent, but the quantum Fourier transform, right? This is a foundational idea in quantum computing, the idea of using a quantum computer to process functions that are defined formally on 2 to the n points in a 2 to the n dimensional space. That's a very high dimensional space. And belief propagation, a very, very old idea going back to Hans Bethe and Judea Pearl, coming from physics and kind of StatMech perspectives about computing partition functions, which could be, say, usually it's classical partition functions, but I'll mention how we can go to quantum partition functions, high dimensional lattice problems. And the idea is that each of these kind of seminal or foundational algorithms can take on a bit of a new twist or a new life when you blend it with a more relatively younger set of methods called tensor networks, which is more of my bread and butter. And I'll go into this in much more detail, but the punchline will be the QFT actually is a tensor network operator, kind of full stop. So it's a small compressible tensor network operator, which means it's a classical algorithm. You can store it in your computer, you can operate with it on your phone. So that's one punchline. Another punchline is that this more general belief propagation method, which I'll introduce and go through the steps a bit, historically has been viewed as kind of like something we would use in the realm of classical StatMech or people doing probability, like studying, spreading of disease on like a network model of people, like network theory might use this or something. But it turns out it's actually can be turned into a general purpose, even controlled method for high dimensional quantum dynamic simulations. This is really new. We don't know how good it is all the way yet, but there's early signs that it's going to give some sort of a new push to that topic. BP. BP. So BP is belief propagation. Yeah, but I haven't defined the steps yet. These are just the abstract of the talk. So I'll get into all these in much more detail. So sort of the motivation for me and this is what spurred some of this work, in fact, is that as many of you know, and many of you all share, there's a great excitement for the prospects of quantum computers, right? It's a really exciting time, especially on the hardware level. So this is a picture of actually a former colleague of mine from Santa Barbara showing the head of Google, one of their fridges holding one of their quantum computers, right? So really exciting stuff's happening. I don't need to tell all of you, even in the last few months, right? There's been breakthroughs in error correction hardware side. And so these works support a very beautiful idea that quantum mechanics itself could be harnessed to solve problems inaccessible to classical computers. So this is just a motivation slide to say, to me, then that asks the question, I'm more of a classical algorithm minded person. So the question for me is, okay, well, what is it that makes problems inaccessible to classical computers? What's sort of going wrong with our existing algorithms that makes these hard, where we might need a quantum computer instead? So the hardware is being built. This quantum hardware is being built, and the progress is rapid and really impressive, especially this year. So then there's a question: what is the best applications to do with these devices? And the goal people have very often is to beat classical computers. People talk about utility or advantage. But one thing I'll even flash a headline later in the talk where there'll be, you'll see in the media, they'll say it's faster than a supercomputer, a quantum computer. But what is the speed of a supercomputer, right? I mean, a supercomputer doing what, right? That's kind of the question. So I'm really just using this as a straw man to kind of set up the classical side, right? Because you could just have a computer just adding a bunch of random numbers together, and you could say, boy, it's really fast at doing that. But of course, there wouldn't really be any value in that, right? So it's really about what you do with it. So my argument here is that classical computing is not, doesn't have a speed, or we don't know the real speed yet, is maybe what you could say. That problems that were exponential, that we only knew exponential approaches to as recently as 10 years ago, even like 2 years ago, are now solvable today with linearly scaling methods. So did complexity theory itself change, or were we wrong about that? No, it's just that it was only exponential because we were doing it in a really stupid way, right? We just didn't know a good way to do it. It doesn't mean there wasn't. We just didn't know. Or maybe it's case by case is another point. So the point is we're constantly discovering new algorithms. So it's not only the hardware, or even primarily the hardware, that's moving this target away from the darts, right? It's the algorithms that's really going on. So there's a traditional conception that you see, especially if you read the media that comes around like Silicon Valley, and people talk about, you'll see stuff like people will be on panels and they'll say, in the future, they'll paint this almost Mad Max scene of like, whoever has the most GPUs will be the ruler of some region, and they'll be almost like trading GPUs like money, and that's going to be the currency of the future. It's a very hardware-centric view of computers. But underneath that view, I mean, it might be true, I don't know. But underneath that view, I think there's a traditional mindset there, some kind of conventional mindset of what an algorithm is like. You hear a lot about algorithms. People talk about, the algorithm showed me this thing on Facebook. And so people talk about algorithms a lot right now. But the mindset I sense a lot from people in the media talking about that is that they imagine an algorithm as like something you look up in a table. You say, what's the cost? What's the upfront cost? And you follow like a recipe, a fixed number of steps. So an example of this would be the fast Fourier transform, is that kind of algorithm where you say, you don't know what problem you're solving. You don't have to know, which is kind of beautiful. It's just n log n, where n is the number of grid points you discretize onto for the Fourier transform, and the cost is always n log n. And you just follow deterministic steps, and there's n log n steps, and you're done every time. And that's a very comfortable conception of an algorithm. But the real world is more uncomfortable. And there's newer breeds of algorithm. I mean, we've had these for a long time, but I'd say more and more we have to face the following kind of algorithms. They're dynamic, they're adaptive. The cost is problem dependent. And because it's problem dependent, you can break these algorithms. They're a little more brittle, and you have to kind of point them at the right thing. So the worst case for these algorithms might be exponential, and that might be really exponential. Like it's not just because we don't know what we're doing. It might just be that hard. However, nevertheless, the algorithm is useful because not everything in real life is worst case, right? You go to a business and they just have the problem that they have. They're not trying to break the algorithm. They just have the network that the traveling salesman is moving on, and then it's finite, and they just want to know, the second best solution for them is pretty useful. So an example of this kind of algorithm would be DMRG for finding ground states. It's actually, you can break it, but if the states are low entangled and nice, it can succeed wildly well and take an exponential size problem down to a linear scaling problem. So that's kind of the, this is sort of my picture of scaling. So this is all about scaling at the outer level. So just to give you one example of recent progress, this is just a quick example. I'm not going to dive into this one on a technical level, but there's a paper I would highly recommend from February by this group out of the UK, Jonathan Keeling and others, where they developed a new one of these dynamic algorithms to actually compute the dynamics, the quantum dynamics of a quantum dot or two-level system coupled to an infinite bath of Gaussian phonons. So imagine like an NV center in diamond, and the diamond is vibrating, and there's this kind of two-level quantum system in that environment. And this algorithm uses compression, actually a kind of tensor network compression in time, and it succeeds due to the existence of structure. So the structure is the finite memory of the bath. It's a non-Markovian method, so there is memory, but the memory decays. And because of that, they can actually time evolve a quantum system to millions of time steps within minutes on a conventional computer. And they have to do this because the system has femtosecond timescales. So to actually get the right results to compare to experiment, this is needed. So there's just like, really profound progress happening even just in the last year in this area. So these are not fixed things, but moving targets. And then kind of lastly in the motivation is that why should you care about algorithms? I mean, one reason is just to crunch out numbers, right? So that could be one conception of, we just want better numbers to compare to experiment. And that's quite valuable. But another reason is that algorithms offer insights, I would argue. So, just earlier this past month, Frank Verstraete was here, and his group has been pursuing a program where, motivated by algorithms based on tensor networks to represent ground states in 2D, you can have a different perspective or kind of a complementary perspective on new ideas about symmetries and about topological phases. So that's just one line of work. And people are using tensor networks, which will be the workhorse in this talk, to do things like classify symmetry protected states of mixed states of open systems. So they're also a source of insights. And I would argue that these points I was making about scaling and about dynamic algorithms connects back to structure. So what makes things computable in practice would be structure, right? Locality, low entanglement, limited entanglement, low order correlations, meaning you want low order correlations and you're willing to sacrifice high order correlations. Even though they're there, you might be willing to make errors in that part of the calculation. Cliffordness, Gaussianity, I don't know if Cliffordness is a word, but you know what I mean. So those kind of connections are there too. Okay, so that's just some motivation. So back to this point about why have classical algorithms not immediately solved everything from the beginning? Like what's been in our way? And the point is that a lot of parts of classical algorithms have already succeeded very wildly well. So what is an example of things that have just succeeded, to everyone's wildest dreams? One example would be solving partial differential equations and computing integrals of complicated functions, but not too complicated. They have to be kind of relatively smooth in 1 and 2 and 3-dimensional space. So this is a picture I stole from the Center for Computational Mathematics at Flatiron's website, where they're showing some kind of velocity field around some kind of obstacles or in complicated geometries. So they can do a lot in 2-dimensional and 3-dimensional space with PDE solving. That's one example. Another example would be sparse data. If you're working with very sparse data, it could but nevertheless be very large. So a very famous example also out of CCM, I'm just kind of using them as an example, is this thing called the non-uniform FFT, where you can run like a CAT scan or an MRI and generate millions of sort of randomly distributed points, but which are snapshots of some kind of smooth image, like an image of your brain, as shown here. And then nevertheless, but even though the data is sort of irregularly spaced out and there's millions and millions of points, they have essentially like linear scaling methods to pull off the Fourier transform of that kind of data. And they can run extremely fast. So very often, if you're actually getting medical imaging done, there's very sophisticated math running underneath of this kind to reconstruct the image. So these are things that have worked really well. But what has not been so possible, even as recently as, up until today? What's not so possible, so in contrast to say 2 and 3-dimensional PDEs, partial differential equations, what about solving PDEs in 6 dimensions or higher? I mean, you can easily think of problems where you have PDEs in 50 dimensions or 100 dimensions, right? That's one example. So there's some recent progress here using techniques I'll talk about later. This is a group at MIT solving plasma equations in 6-dimension space. So there's been some progress there, but that's been historically very hard. Another example is classical rate reaction dynamics of chemical species. So I mentioned some of this to some of you the other day. So this would be like, imagine just, different chemical species mixing together. And this is just classical master equation stuff, no quantum mechanics, but it's still very, very high dimensional. And of course, many body physics. I would say as a sidebar, it's not like you can't tackle these problems. I mean, people have been. It's just that some of the tools we have, for example, Monte Carlo, they're very often directly applicable to these problems, but the trade-off is that they're very expensive. You have to parallelize them on huge supercomputer centers, and the power bill is gigantic. And you have to wait for days and days and days just to get 2 digits of accuracy. They might be very low precision results. So sometimes this just doesn't cut it for state-of-the-art scientific work that you have to do. And the challenge here comes from the high dimensionalness of these problems. So I'm just picking one example, this rate reaction stuff. It basically is nothing more than a problem like this, where you have populations of chemical species or these discrete values, I1, I2, I3, how much hydrogen do you have? How much oxygen? How much, like each kind of atom or molecule do you have? And it's evolving in time. These populations are evolving in time. There's some kind of master equation that's just some matrix of transition rates. Like think of like a Monte Carlo, like a Markov chain you're running forward. But the point is that even just storing this, when you have lots of species and they're divided up into spatial regions, might become exponentials, even just to store the result, much less to compute it. So something as simple as that, just classical master equation, right? So now let's think about mathematically, why is this exponential to store and compute with, and what sort of a formalism we can use to cover all of these cases in a single formalism. And the formalism will be that of tensors. And it turns out you can use tensors as this kind of universal picture that you can understand many of these problems in terms of. So one point is that tensors, you might think this is linear algebra. We think of the Schrodinger equation, right? We say it's a linear equation, which it is. But importantly, it's in a high dimensional space, right? As we all would know. And so importantly, any function of discrete variables can be stored inside a tensor, no matter how nonlinear the function itself is. The function could be a very nonlinear function of these variables. So the linearity is happening in kind of a much higher dimension than the actual shape of the function. So the function can be arbitrary, right? So any function of discrete variables, we can fill out the tensor with the values, all the values of that function, right? So for example, someone says, give me, f of 1, 2, 2, 2, 1, 2. That's just an entry in this big tensor. I can reach in and get that. I can store that. I can store that entry. I can store any entry I want, right? And importantly, yes.
We had some introduction to tensor networks, so you can go.
I can go kind of fast here. Yeah. Sure. Okay. Absolutely. Yeah. But let me make the point. This also might be pretty obvious to a lot of you that you can also input continuous variables into a tensor. You can map continuous functions. So if any of you know the very old idea of amplitude encoding, this is all I'm talking about. But let me review that idea real fast. So say you have a function of one continuous variable. Well, as we know, as we always do on the computer, say if the variable is between 0 and 1, it has a decimal expansion. You can expand it into decimals. And then these decimals are now integers. So we can just use the previous slide where a tensor can hold any integer value function, right? So we could say f of 5, get me f of 5. Well, I would just set the external indices to these values, 5, 0, 0, 0, 0, 0, right? And I could store that. And there's room to store f of 0. I just set them all to 0. F of 1 is just set them all to 9. F of 3/4, and then you can make fine movements on this grid too. So you see underneath, I'm locating on the grid where these points would be in continuous space. So, I can also, by changing the last bit, I can move by 1 grid point or 2 grid points. So you can make fine movements and coarse movements by toggling the leading digits or the subleading digits, right? But the point is that, you think of these things as maybe being linear and discrete, but actually it can also be nonlinear and continuous if you kind of project back to low dimensions and think that way. Okay, I'll go a little faster through this part, but as we know, wave functions, many-body wave functions are this kind of problem, like the amplitudes of a many-body wave function is just a kind of large tensor. So my point of this is just to say that high dimensionality could actually be high dimensions, but it could also be one dimension that's continuous, and it's the same size of data in principle. It's the same kind of space. So a lot of the tools could be shared across these two types of problems. Okay. And so we know these are exponential to store, and then we could use tensor networks to try as one strategy to try to deal with these kind of exponential objects. There's other strategies too. You could posit that maybe these are sparse, you could do sampling, but tensor networks are particularly appealing. So let me go on to say that a tensor network will use this notation that I think a lot of you know, where we say a tensor is a shape and the indices are these lines coming out. So, matrix would be 2 lines, third order tensor would be 3 lines. We can join the lines to say that we're doing a contraction over the tensors in the network, right? And it's a really nice notation. We don't have to write things like this. We can just express them with diagrams, but it's exactly the same information. Like the left and the right, there's no difference in what information is being presented. Great. So, and the idea is that these are motivated too, right? So they come from the idea of a low rank a matrix. It's just a lifting of linear algebra to very high dimensions. So there's an old problem in matrix theory where you say, find for a given matrix with specific entries, find it as write it as a product of 2 other matrices and try to make the new index shared between them as small as possible. And you try to solve this problem under different norms. Like you might try this under the 2 norm distance between A and B back to M. There's the nuclear norm distance, you can use different norms. And all these are solved by the singular value decomposition across multiple norms. So it's an optimal solution for this problem of breaking the matrix into 2 pieces and trying to compress. So that's sort of a subroutine that's always available. And you can apply it to a matrix, which I show in this slide. So this is just a matrix 2 indices. And you can cut it and you can talk about its rank or proximate or exact rank, which would be how small can we make this new index connecting the 2 factors. But then a nice thing you can do is you could say, well, a tensor can be matricized. We could treat the first index as a kind of row, and the rest is some kind of collective column of many indices. And we could do the same kind of low rank factorization, whether in SVD or another way. But then this is hierarchical or recursive. We could say, well, that remainder is just another tensor. We can split the first 2 indices off and do it again and again and again. So what we can do is we can unzip structure out of a high dimensional object. We could just imagine recursively going down. And then if the data is friendly in this object, if the numbers are, have a patterns or structure, then the ranks that we get pi, we call them the bond dimensions very often in physics, might be small. They might not be, but it's problem dependent, right? And so we can get a huge advantage, in fact, an exponential one, if these turn out to be small. So in the worst case, they'll be exponential, like 2 to the n over 2, if all the external indices are dimension 2, but sometimes they won't be. Sometimes the chi might just be low, like a 50 or 100, depending on what data you have and what accuracy you need. And most importantly, there's beautiful algorithms to work with these, and they very often scale like chi cubed cost to do certain operations. And maybe the storage is just chi squared. So many algorithms we can do. We can add these objects staying always in the compressed form. We can multiply them with operators that also have this kind of structure. You can do perfect sampling over them. Yes.
I was just wondering with the compression and like the example you gave before with the continuous function, like what sort of, if I just give you some distribution and I actually do exactly what you said with the digits,
It's a good question.
Is that a compressible?
Yeah, like some particular example of a function.
Yeah, or is it known like what kind of functions?
It is. So I'm actually going to exactly come to that in a few slides. So it's a good question. So for example, any smooth 1D function would be.
Any smooth, okay.
You can prove that. And I'll give a few more cases too in a few slides. Thanks. So I'll come right back to that real soon. So the point is there's this nice toolbox that we have. So all that's to say that, I'm making it all sound great, like, exponential compression, lots of algorithms, right? But as many of you may have heard, you would have heard if this works for everything, right? Because we would have already solved all of your problems, right? So obviously this doesn't do everything, right? So what doesn't work right now with these tools? We can do a lot. We can do 1D, we can do dynamics, but what has been hard up until recently? So one problem that just hasn't been tackled very much is inputting continuous variables. So that idea I showed a few slides ago was popularized about 10 years ago in the applied math community, and it's been known to the quantum computing community, but it hasn't really been picked up much by the many-body physics community, even though it's just been there sitting on the table for a while. So that's not been explored very much. Another one that's even more dire is working in higher dimensions in terms of spatial dimensions and time dimensions, is dealing with 2D lattices. Right now, we have good tools conceptually, but they're just too expensive. So the prefactors are too high, the scaling is too high. You can push on easy problems a certain amount, but you just hit a wall, the precision is low, the times are long, the code is complicated. So it's just been kind of a slog. And then 3D there's been some attempts at 3D that have been quite great, but limited. And then people have been very reluctant to attempt dynamics in 2D and 3D for that reason, because it's already hard enough just to say even extract the properties of these states in 2D. So don't want to get into dynamics, if you can't even measure observables. So this has been pretty frustrating. especially over the last, say, 10 years, because there was a lot more enthusiasm before, and it's been a little bit plateauing. So now I think there's some hopes that we might have unlocked some of these jams, dealing with continuous variables, dealing with high dimensions, and I'm going to explain why I'm pretty hopeful and what are some new developments. So, okay, so new development number one is how interesting these are when you work with continuous variables. You know, what you can do and what algorithms there are, and then how that connects to some existing ideas, and specifically the quantum Fourier transform. So that's what this part will be about. So as I said a few slides ago, there's this pattern you can use to input continuous variables in tensors, right? And you could, of course, do more than one. I'll kind of get to that, but this is just showing one continuous variable turns into a small collection of indices. So you'd say a single input like X or Y or Z turns into a group of 10 or 20, you know, two-dimensional indices that they work together as a group to represent an input. And we've also talked about how, given a tensor, you can decompose it in a kind of low-rank way as a tensor network. And there's different kinds, but this is a matrix product state 1D tensor network. So we have these two capabilities. So exactly to your question a minute ago, what happens when you actually try to use those together? So you say, I know, you know, I can input to a tensor a continuous variable, I can decompose a tensor. Are these happy together, or like, is this actually a fruitful direction to go? And when does it work? When doesn't it work? Basically, what continuous functions have like low entanglement, right? And this in a way hasn't been tackled that much, because there's been a lot of proposals, as far as I know, in the quantum computing literature, say to solve PDEs in a quantum computer. But I'm not as aware of results saying, for this given PDE, will the quantum computer at the end be highly entangled? Like, will you actually need all that entanglement power to actually store the result? And so it turns out that there's been some recent work showing that quite a lot of cases are low entanglement. So all smooth functions can be shown to be low entanglement. And then, say in the case of 1D functions, one variable functions, even having a finite number of cusps or sharp discontinuities is still okay. So basically, for every cusp you put in like a 1D function, or every discontinuity, the bond dimension or rank just goes up by 1. So you have 50 cusps, just add 50 to the bond dimension, which is really not very much, actually. And then any Fourier transform of these as well. And there's many other fast algorithms you can do. You can do fast convolutions, you can do efficient Fourier transforms. So there's actually a whole zoo of algorithms that you can develop. Some of this has been happening so fast, it's not even really written up yet, but it's like really fun to actually figure out how to represent the operators in this language and everything. So here's some very concrete examples. It turns out that exponential functions are product states in this language, and so are delta functions. So if you think about the rigged Hilbert space, you know, Dirac's famous kind of dirty corners of Hilbert space, those two rigged parts are actually the product states in this language, which is, I find, kind of interesting. And then since a cosine is two exponentials, trig functions have exactly a bond dimension of 2, all single cosines or sines. And then there's a theorem about tensor networks that says if you add the functions, the bond dimensions add in the worst case. So then you would think if you added 20 cosines that the bond dimension will be 40. But actually it's 18 in this case, because it's a smart compression algorithm. So we picked cosines where there was some relationship between the scales, like some of them had slow oscillations, some of them had fast. So you can actually compress more than the worst case and get a really nice compression. You can add some cusp, try to make the function really bad. The bond dimension barely grows. So it's very powerful. You could ask, how do I make this not work? Like, what would be the worst case? And so remember, there's a fine grid here, which is, it's got like a 1/2 to the n spacing if I have n of these bits. Like, so we actually do space 2 usually. And each of these lines would represent a bit in the kind of binary decimal expansion. So there's 2 to the n grid points that I'm plotting here in this trick. And the worst case would just be go to every grid point and just put a totally different random value on every grid point that has nothing to do with any of the other. So basically just noise. But that's the case that doesn't compress at all.
Does this depend on how many digits you are considering the precision?
It really doesn't. I mean, when the worst case it would. Because then if you put noise, it's the bond dimensions will be exponential in the grid size. You just have to store the whole grid. And since the grid is going to grow exponentially with the number of bits, then it will grow exponentially with the length of this string. But in the best case, it's like everything is logarithmic in the grid size. So everything will just be linear in the number of bits in the best case with this idea. And then that's the log of the.
So you're saying the chi was from logarithmic?
Well, in the best case, the chi would be like a constant. And so then the cost of the work is linear because you have to at least visit every tensor once. And then linear is n, and then this grid is 2 to the. So it's a log reduction. It's like taking the log of the grid.
Are these translationally invariant?
They can be. These are kind of fun things that we've been thinking about, like how does this translation invariant manifest here in some kind of nice way. I don't think that kind of stuff has been honestly explored in a really careful way yet. Like if there's something deep to say there or not. But it's really easy to make them periodic and translation invariant. But like it doesn't make the bond dimensions worse. It's kind of the same. So yeah, good question.
So the good or bad cases are for the 3 cases, or
these are just 3. These are all good.
okay.
Yeah. Bad would just be if instead of seeing this nice smooth shape, if you just saw just random noise, like just white noise or something, just static or something like that. Yeah. And then one nice thing about it too is that I'm showing you these 1D examples, one variable. So you might think 2 variables, you have to use these 2D tensor networks, which are very hard to work with and difficult to manage. PEPS tensor networks, if you know those, but you don't. 2 variables is just every tensor has 2 indices. That's 2D. And 3D would just be 3 indices. So it's very mild actually to do 2-dimensional space, 3-dimensional space, right? Which is already quite useful, right? Because we could represent 2-dimensional data, 3-dimensional data, functions that are solutions of differential equations involving, fluid flows and all sorts of real science applications, right? And they're just little matrix products. So it's actually a very handy idea. So that's just representation. Yeah.
But what's a chi? How is the chi changed if you change dimension?
Yeah, it can be tougher in 2D and 3D though. You're onto something. So there's more ways it can go wrong in 2D and 3D than in 1D. So one way it can go wrong, it's kind of cute in a way. It's like these authors who wrote this preprint up last year, it's published this year, were compressing some functions encountered in physics. Like this is a particular single particle Green's function that they were compressing. And it can kind of fail when you're at 0 temperature and have a Fermi surface. But it's not due to physics per se. It's just due to the fact that you have sharp steps. So if you have kind of like a mesa shape, like a plateau that has a fixed value, and then it just drops very steeply, but the shape is not a square. That's just some rounded shape. This can blow the bond dimension up by high. But you can smooth the function if you just regularize, like smooth the function a little bit, put in a little bit of temperature, and the bond dimension comes back down. So it's just kind of a cute fact about these. But they're already using it to do things like computing Chern numbers from band theories of free fermions really accurately and things like this using these tools. So you can do like line integrals, and it's actually a very handy tool even for that kind of stuff. Okay, so that's just all about, yes.
What does the operator, the exponent function look like in 1D and 2D?
So what do the operators look like?
Yeah, derivative.
Yeah, so I'll be talking about one operator in a second in a little bit of detail, which is the Fourier transform. But it's really fun. I mean, I could give a whole hour on just the operators. We were even thinking of writing just a little survey, because I think the results right now are a bit scattered around papers. We'll read papers where they'll say, you make the derivative in kind of the obvious way that you would, but they don't show you how, And it's like, it might be useful to just have a review article. So for example, it's pretty fun. So the way a derivative works, for example, is that you actually come up with an MPO tensor network. So these are these tensor network operators, chain of tensors, that is a shift operator, shifts by 1 lattice spacing. And it turns out that operator is the ripple carry algorithm that we all learn in school. So when you're learning as a kid to add in base 10, and then you carry 9 and you carry over to the next place, that's the entanglement. So the bond dimension is the carry. So it's bond dimension 2 because you can only carry 0 or 1. So it's exactly bond dimension 2 MPO because you do ripple carry to shift all the bits by 1. You shift all the grid points by 1. Then a derivative, you can use what's called finite differencing formulas. So a derivative, like second derivative, would be shift to the left plus shift to the right. And then also there's a constant term, and then you divide by the grid spacing. So it's an MPO of like bond dimension 5 or something. I think there's a little extra compression that happens. So you just come up with these rules. Integration is like a product state that you just slap onto the function. And then you can also do indefinite integrals. So you have the entire toolbox of calculus, all is low bond dimension. BO objects. So it's really fun. So
Sorry, what would be the picture for some function that contains the branch cuts?
that's a good question. So I think basically nobody has tried with complex variables very much. Some postdocs I work with have tried it a little bit, but I think there've been very little, very little serious investigation of whether it's how interesting it is to get or not. But it's very straightforward to try. So I think someone should try. Yeah, I think a single branch cut would be no problem. Is my feeling. Yeah. I think there's even people talking right now about using this for math questions, like, trying to store, the Riemann zeta function in this format, something like that, and then see if you can get insights into sort of math problems this way. So I think like Herman Sierra in Spain is interested in this sort of thing, and Jose Latorre have been, talking about this a bit out at like the Simons Center for Geometry and Physics and things. Yeah.
Is this connected to wavelets in any way?
Actually, it is and isn't. So it's sort of, my current take on it is that it brings everything you want from wavelets, but it's slightly better. It's kind of my current feeling about it. Like it's multi-scale, and it brings many of the same capabilities as wavelets. And also you can actually write many of the wavelet transforms as MPOs. It's pretty straightforward to do a construction where you can write the wavelet transforms. So they all kind of fit really well into this language. But I would say in a way, it's almost like an alternative to wavelets in many respects. Yeah. Yeah, thanks for all the questions. Great. So so that's the representation side. So I just gave a few results verbally about operators. Let me walk through the one that this is really what got some of us into this business. Was we were actually trying to take a bit of a swing at quantum computing and just see what we could simulate with some of our codes. And so we weren't thinking about these functions. We were really thinking about the quantum Fourier transform. And then we realized some of this other stuff about the functions. Not only us, I mean, there's been other groups recently doing this too. So when you're thinking about these functions that are tensorized functions, as I'm calling them, you could say, well, what's the operator for the Fourier transform? And you very quickly realize it's the quantum Fourier transform, because this is nothing but the amplitude encoding framework people use for like HHL algorithms in quantum computing, all of that same setup, just with the extra twist of tensor networks compression on top. So the quantum Fourier transform it's just the same one that you might have heard about. That's the second half of Shor's algorithm for factoring. So this is just one slide where I'm showing you a cartoon of Shor's algorithm. There's this modular exponentiation part. Then when you're done, you extract the results using this QFT circuit. And I'm not going to go way into the details of the circuit. It's just a bunch of controlled phase gates and some Hadamard gates and things. But what it does mathematically is if you think of the function as being unrolled into a big vector, like a big state representation, it's just the discrete Fourier transform matrix. It's just a matrix full of phase factors like this, depending on what row and column you're in, it's just different phases, right? It takes you to Fourier space.
So does this mean that quantum Fourier transformation can be done purely classically by the?
That's what it'll turn out to be exactly. So I'll get right to that in one or two slides. So thanks. So the idea is that every quantum circuit actually is a tensor network, full stop. You can just very easily translate gates into tensors and single particle gates or matrices. That's not anything new. So you can write a tensor network for this kind of famous QFT circuit. And we actually had a really talented undergrad, Jilan Chris Chen, do this when he was an undergrad at Irvine just a couple of years ago. We said to him, there's Chris. And so we said, please just translate every part of the circuit into a tensor, the straightforward way that you just would. And we had a code already for taking columns of this tensor network. To us, that looks like an MPO tensor network right there. There's another one there. There's just a single qubit gate. And just multiply them one after another using some algorithms we have that multiply MPOs and recompress them. So this was one of the first times he had used our code. So he ran this and he said, okay, I'll just multiply them pairwise across. And every time he would find that the internal bond dimension or rank was about 10 or 8, and we would tell him, turn the accuracy up, that can't be true, turn it up higher, it'll definitely grow. And he would turn it higher and higher and higher accuracy, and it would just stay at like 10 every time. And then we would try more qubits, to go to 40 qubits, and it was still just always hitting 10. So then we kind of dug into it, and Chris turns out is kind of a monster, and he was able to prove rigorously bounds on the decay of the Schmidt values of the operator. and show all these really interesting mappings. Like, for example, you can map this onto a different operator that provably generates the same amount of bipartite entanglement, but is actually like similar to evolving in time by a time of pi/2 of a certain Ising model Hamiltonian that's short range. So he has all these really nice arguments that he put into the paper. So I really recommend reading about that. And basically, it's now proved that the QFT for any number of qubits to very high precision is MPO, like bond dimension about 10. It's formally infinite, but you can always truncate it at about 10, no matter the number of qubits. So it really brings it back into the classical world. It's really a classical algorithm all along from that view, kind of to your question as well. And so then what can you do with this classical algorithm? So one thing we wanted to try was not to do the fast Fourier transform, but try to do super fast Fourier transform. So can we do the Fourier transform in log time instead of n log n? Can we just do it in log n time? And you basically can. So you do it in 2 steps. You prepare your function as one of these tensorized functions as an NPS. Then you apply this QFT, which you've made ahead of time already. And so we tried this on different cases. So first of all, here's the baseline, which is we try grid points growing. I think they got shifted over by accident. But we try grid point that size is going like exponentially finer and finer and finer. So we have 2 to the 4 grid points up to 2 to the 26 grid points. And the FFT scales roughly linearly in that number. So you see it just kind of shooting up the cost of the FFT. The FFT is a black box. It doesn't know what function you're transforming. It's a very good algorithm, but it's just agnostic to that. This kind of super fast framework with the MPOs and the tensor networks is very, very sensitive to what function you're transforming. So we inputted these functions that were either very easy or sort of moderately difficult, and the prefactors are higher. So at first it's slower, but these are very small problems. But then there's a crossover. So it basically just barely cares how fine of a grid you're on. You can just go to the continuum limit, and the cost is all very fast, and the FFT is exploding. So you can get it to be really as fast, much faster as you want. Here it's like 1,000 times faster where we stopped. And the point is that this isn't violating any theorems or anything because it's problem dependent. So there's no total free lunch here. If you put in random data, you can't compress it at all. So even the first part already scales exponentially, much less the Fourier transform. So it's this new breed of algorithm I was referring to where it's very dynamic, it's very fun. So I thought that was kind of fun.
This time includes the initial compression of the function.
It actually does, yeah.
Yeah.
Which is kind of neat, yeah.
Yeah, well, yeah.
Exactly, and we did the compression in a pretty naive way. And by now, there's actually much better ways to do it. But even with a pretty naive compression, we could get this kind of speed up, which is interesting. So we've been asking ourselves now, are there actual like real life workloads like the MRI example, something where you could actually use this? And so we're thinking about this. I think there might be something like that.
Confused. So I would have expected you needed n just because you need to read the function at n values.
Yes, right. Okay, sorry. Sorry. These curves are not including the loading time. You're right. So when we include the loading time, it of course has to scale that way you said. So this is the plot without the loading time. We can still beat the FFT even when we have the same scaling. We can get a better overall time, but you're right. It has to have that scaling to load in the worst case. Now there are algorithms where you can scale purely in like log time for structured functions. So if it's a sum of trig functions, we can do always those in the sort of log time. There's another algorithm I won't have time to talk about that's quite amazing called tensor cross interpolation. And it's actually a fully linear algebra-based machine learning algorithm from the math community that learns matrix product states by sampling points of the function. And it's like an intelligent sampling. It's an active learning algorithm. So it actually picks points and interpolates through the ones it picks. It checks the interpolation locally on a few test points. And if it's good, it stops. If it's bad, it zooms in more and gets more points. And it also cleans away old points. So it's like a very neat algorithm that can learn functions in the same kind of log scaling for quite complicated functions. So we use that too sometimes. Okay, so Chris gave a nice colloquium at Berkeley about this. I'm just putting this so there's a link in the slide. Recommend that to all of you who are interested in the more like rigorous aspects, because there's a lot of really nice proofs that Chris pulled off about the scaling of these operators. And then later, he also worked with Michael Lindsay just earlier this year, who's a new math hire at Berkeley, and they actually derived an exact formula for the operator. So for any remaining skepticism people had about, is this really right, or is this just a numerical result? There's an explicit formula for the tensor cores of this operator in terms of the set of polynomials and some phase factors that you can just directly code and work out. So it's a really nice result by them. And then just ending this part, this is now kind of one piece of a larger activity that's been going on. Some of this preceded this work of what people are calling quantum-inspired classical algorithms. And it's really just the idea of tensorizing functions and using them for all sorts of problems. And so one that's gotten quite a bit of notice is fluid simulations. So these are solutions of the Navier-Stokes equations, incompressible Navier-Stokes in 3D. And the top line is showing a state-of-the-art grid-based simulation. And the bottom line is actually a matrix product state. So that's just getting the same result of a certain vortex flow configuration that is like a popular benchmark. I already mentioned storing functions people use in physics calculations. And there's even work people are doing where they're thinking about basis sets that people use in quantum chemistry, where they use Gaussian, like superpositions of Gaussian functions, and trying to go back and say, what if we use tensor networks as basis functions to do Hartree phi? So it's kind of weird because you would think, okay, there's an MPS that are going to do DMRG, but you can actually use MPS to set up a Hartree phi calculation, and that's it. But you might have better resolution of the continuum using these kind of more modern basis sets made out of tensor networks. So there's all these kind of different ideas mixing together at different levels that people are trying. Okay, so that was kind of just that part. I think I probably went bit off a bit more I can chew with time, so I'm gonna do this part pretty quickly, but slow me down if there's questions. But so that was about one kind of algorithm family that we're like bringing a new life. The other one is about this BP idea and how we can use it to tackle higher dimensions of tensor networks. So the motivation here was also quantum computing. So that's kind of a similar thread for us, is sort of taking on quantum computing a bit as a challenge to see how far can we keep pushing our algorithms, right? So there was this paper that appeared in Nature last summer where IBM, a team at IBM, had used one of their newer devices to simulate a certain quantum dynamics. And the coverage was pretty fierce in saying that, they did something that classical methods can't reach. That's right on the cover of Nature. Another coverage said it beat a supercomputer. So, that we were pretty interested in what they did. What did the experiment do? So this is a schematic of their processor. So they have all these qubits arranged in the following layout. And what they did is a kind of stroboscopic or flow K dynamics, where they first apply this operator, which takes like a unit step in time with the ZZ part of an Ising Hamiltonian, and then this part, which is like a transverse field part, where theta is like the field strength, and they can tune different theta values and do the experiment. So they do a set of layers of these up to something like 5 layers, up to 20 layers, repeatedly applying this kind of flow K operator. And the qubits, of course, are being treated as Ising spins. So it's like a transverse field Ising model with pseudo-randomness. They go first to shallow depths, where the blue points are their error mitigated results for operators like expected value of sigma z, or these very high weight operators. So they have x on all these positions and poly y on one and z. So it's these very, very high body operators as well. But these are all at shallow depths, so they could get exact results. And they compare it importantly to 2 different tensor network methods, matrix product states and a certain kind of PEPS 2D tensor network algorithm. And the tensor network algorithms are really struggling. They kind of work at the small theta, but then at larger theta, and for certain properties, they're just missing by giant amounts. It's really bad in some cases. So they said, this is offering utility over existing methods in certain cases.
What is
Yeah.
what is diagram? Can you explain the axis?
What are the axes? So the axis is this theta field, transverse field strength, defining the circuit that they run. And then the y-axis is just the expected value of certain operators, like either sigma z, poly z, or products of poly x, y's, and z's on sort of funny clusters of sites, or
It's a correlation function.
kind of. I think they're just some kind of rather arbitrary high weight poly product. It's a bit made up, I think. Here they're sort of designed to just be hard to compute, I think.
States, expectation value in which state?
In the time of all states. So after you apply this u some amount of times, in this case, these are,
Product state.
you start in a product state and you apply the u on the quantum computer some number of times. Here it's a few times, like 5. And then you take the expected value of, they do it through sampling, of course, and you get expected values of these operators. And then, with the classical methods as well. So these are the shallow depth. And then they also did much deeper circuits, I think, in the 20s. And then the tensor methods are just not keeping up at all. you had a question too.
Was this particular model important for this, or is just some unitary they chose?
That's a good question. There are some details of the model that were very favorable to the hardware, which I mean is a good idea, right? You should always, pick, play to your strengths, right? So, but my understanding is that, I mean, we do this too, right? People focus on the problems they're good at to show what the methods can do. So I believe, in particular, this coupling, this ZZ, is very like natural for their hardware. Like it's actually something the hardware would do even when it's idling, is my understanding. So I think changing the model could make things quite a lot harder for them.
This thing has that, is this the model that has the is this at the self-dual point or something of this?
There is a Clifford point in this model.
No, but there's like the more general dual unitary point. Oh,
I don't, possibly, I don't remember about that aspect of it, so I can't say. But there's a Clifford point too, where they could use to get certain predictions about, I think it's at pi/2, that they could use to make certain predictions. Dual unitary maybe, but I can't remember. So I think some of this, is just to say, MPS can struggle because you have to zigzag through the lattice. PEPs can struggle, which is fully 2D tensor networks, but because they're very expensive. So they in principle should work, it's just you can't push them as far as you would want. But somehow, what happened is we were able to simulate the experiment using some modern tools. So how did we do it? So we also did a PEPs, but we chose it not to just be an arbitrary shape, but we chose it to match the exact kind of topology of the same lattice they were using. So did the other group. I'm just saying that's a good starting point. And here's the part that's kind of connecting to belief propagation and kind of this newer view. So if you've ever, not that many of you have, but if you have looked at belief propagation, it's really traditionally presented as being for a classical system, classical partition functions and probability distributions. So how do we get into that setting? So the way we get into that setting is, it's like the Born rules. So we work with the partition function, which is just the fidelity network. It's like take the quantum state, overlap it with itself, and it's unnormalized. So we want to calculate the norm, just like you would want to calculate the partition function of a classical StatMech problem, something like that. So we also have a scalar network, just like you would if you were doing StatMech. But for us, we call it norm network. It's just the norm of the quantum state that we want to compute so we can properly normalize our operators. And once you can compute this number, every other property that you want to get is usually a pretty trivial corollary of being able to do that. So in the process of computing this network, if you want to compute an operator, you just leave a certain tensor for the last one, and you compute everything else down to it, and you have like a hole, and you can put the operator at the last minute and get expected values as well. So all the properties are sort of a corollary of, can you do this contraction? Can you get this number? That's all you really have to be able to do. So how do you do that? So you think about, this is exactly how Hans Bethe was thinking about it too back in like the 30s, would be you leave one tensor for last. You think of that one as occupying a cavity. Some people call it a cavity method. And you want to contract all the rest of the tensors down. So that's what we call the environment. It's the rest of the network contracted, leaving out this one cavity. So the point is that that's also just a tensor with 4 indices. So the one that goes there has 4, this one has 4. So it's just some small tensor. The problem is it would be exponentially hard to obtain the numbers inside of it, even though it's rather small, right? So it's not an easy problem. So what belief propagation does is it says, again, if you had it, you'd be done. Belief propagation says, let's just assume for some reason that small 4-index tensor is actually an outer product of 4 vectors. Why not? That's not true, but it makes things possible to compute with. And those vectors, for whatever reason, are called messages. It's just a jargon that people use. You'll see why it's a good name in a second. So it's just kind of like a mean field approximation. It's not really justified. It's just an uncontrolled thing that works sometimes that you can at least do. The point is that it actually can be justified in certain cases. If there's no loops around the cavity that you're computing, it can be exact. So this entire region up here, if you could contract it, can fit into one of these vectors. And this whole tree section down here can fit into this bottom vector. So there's cases where it's exact, which is when you don't have loops, or when you can ignore certain sets of loops. But in practice, it's just an algorithm. And the idea that's pretty recent is to try this on quantum systems. And what you do is a thing called message passing. So you cut all the loops with these vectors, these messages, which is just like a mean field step. It's just a nonsense. But then you don't know what numbers go in the messages. You just put random numbers into them, and you have to somehow find good numbers. So the way you do that is called message passing. You say, let's improve this message. So what you do is you open up that leg, you contract these 3 tensors onto this core tensor of your wave function or your norm network. that makes a new vector, and you pass the vector over to the next tensor, and it replaces that other vector. So this is how the self-consistency works. So you can see this is actually very easy to program and to implement. And it's very easy to do in 2D, 3D, on all kinds of different lattices. It's very flexible. So you do that again here, you open up another leg, you contract, you shoot another message over. So now we have two messages updated. You can do it downward, and then you just keep doing this around and around and around. You can do it in parallel. And after a while, they all converge to something. So they all stop changing pretty quickly after a while. And then once they're converged, you've now successfully handled the loops. You've now like isolated individual tensors and made things tractable. So now you can do things like applying a gate. You just open up this leg, you apply the gate, you contract all the tensors shown in this little small network. This is cheap to do. And then you recompress, you update messages, and you just keep going. So you can do dynamics on top. And the really important thing is that all these other previous 2D algorithms for tensor networks have a very rough scaling. It's like bond dimension to the 8. But this method is bond dimension to the 6. So that's a big deal. So if you actually go through the numbers, this means that currently we could only reach these bond dimensions or ranks of like 16 or 20. Now we can do like 100. So this is a giant leap forward in terms of our ability to handle more complicated problems. And you can run dynamics on top. So punchline here is that we use this, and in just a few minutes on the computer, we were able to match the shallow circuit results for this quantum processor. So these low weight observables at the high weight observables. So the crosses are the tensor network BP results, and the circles are the quantum experiments. So they're all matching. And then for this larger depths where the other tensor network methods couldn't go, our method is actually more accurate than the quantum experiment. So all the points agree except for one, which was later checked with a few other methods, and you know, the classical methods were correct. So all these calculations in the end only took about a day on a cluster node, and with a few little tricks and bells and whistles, and we were able to beat that result. So we're very excited about what this method where it may take us. So let me
But is it still faster or slower than the computer?
That's a good question. I mean, I think ultimately the quantum computers have a bit of overhead, there's a lot of sampling overhead. I think you also have to think in terms of, payroll, power bill, sourcing parts, classical computers are a commodity and they're widely available. So, also programmability. I mean, like we could do the Heisenberg model with very little change to our code. We could do 3D. We don't have to worry about control wires coming into our fridge. We just program 3D. So I'm talking kind of big. We have a lot of work ahead of us. We've only tried this little outing with the Ising model. We have a lot more work to put our money where our mouth is on this, but we're just excited that maybe new stuff is possible. Yes.
Is this message passing, assuming infinite boundary?
You can do it on finite systems and you can do infinite. It's kind of interesting to relate these to each other, but both are available.
But your explanation seems like you're doing until it's saturated, so it seems like.
Yeah. We were just doing finite size though. So when you reach the edge, the vectors, you either just don't have the messages of the edge, or you can put sort of trivial edge messages that are just fixed and they don't change. So you can handle finite size pretty well. It's a good question. Thanks. So let me wrap up and say, we could talk about the physics of the system of why I'm just short on time, but we think that system turned out to be particularly easy, as if the loops are there formally, but they just don't play a role in the properties. That's sort of our physics punchline. That's that system. So this kind of very vanilla, zeroth order belief propagation is effective in this case. It's not going to be effective in every case. So then the question would be, what are we going to do when it doesn't work, right? Do we just go back to the expensive methods? Here's what we're thinking about instead. So this paper just appeared 2 weeks ago or 3 weeks ago out of Caltech and Amazon, where people are now developing corrections to this method. So it's very neat. So you start with your kind of vacuum where you've kind of isolated all your tensors with these vectors. This is very cheap. And then you can make systematic corrections. So it looks a lot like Feynman diagrams or series expansions, high temperature series. It sort of has these flavors, but it's all inside of like a quantum ground state or a state that's evolving in time. And how do you do it? You have your messages you've computed, then you just have a kind of complementary space. So this red line is a rank, chi -1 projector that projects out the message space. And you can show that only closed loops contribute. Open loops gives you 0. And then these are cheap loops. You can just compute these small loops in a very cheap way with the same scaling. and do all these other things on top, like the dynamics. So you can now kind of actually turn this uncontrolled method into a controlled method. So this is pretty exciting thing. That's one thing. Another quick point, this is just, I have to,
uncontrolled, the previous one?
the previous one's kind of has a flavor of like a mean field theory in the sense that you just get what you get. So it's like doing Hartree-Fock or something.
Also, you don't have a suspension where you treat the corrections?
You don't get an error bar, you don't get a report saying you can trust this result or you can't.
Oh.
You just get a number. It's like doing DFT or something. So, but now we actually have a hope that you can get a flag will go up if it's wrong. So we know not to publish the result if this error is big. Or if it's small, we can validate. We can say, we know we're right, and without having to check against quantum computers. So it's very, very handy to have. But more importantly, we can actually improve our results. Right? These loops, in the best case, the contributions decay exponentially. You can show that. So these ideas are already being put to work. So just last week, another paper came out where one of the big proposals for using quantum computers is quantum annealing. So solving problems like, max min and max cut and these kind of things where you use QAOA or these ideas to try to solve graph problems, mapping onto Ising models. So this group is using this kind of exact tensor network BP framework and tackling problems with 1,000 qubits, 10 to the 6 gates. And they're coming in, second and third against state-of-the-art classical heuristic methods and things like what you could do on a D-Wave. So there's some very interesting kind of cat and mouse competition going on right now between classical and quantum using these ideas. One other thing I just thought I would throw in is something we're working on, which is back to those continuous variable mappings. I think they have really interesting possibilities for tensor network applications to continuous variable lattice models. So say taking the XY model, unrolling the thetas into bits, which makes an extra dimension. And now it's a discrete tensor network in 3D. And you can think about the symmetries and they're actually strings. So when you want to say what's the U1 symmetry, just the regular old U1 symmetry of the classical XY model, it's actually done by passing MPOs through the network. So there's just some fun other directions you can do besides solving PDEs with this kind of bits to continuous variable stuff. So I just mentioned that if any of y'all want to discuss. So thanks for your attention. I'll just leave up my summary. Thanks for the many questions already. Great. So I know there are already a lot of questions during the talk, so thanks for those. If you have any more, though, be to take them.
Can you go to a slide where you do this cluster expansion each thing?
Yeah, this is by Garnet Chen and Glenn Evanbly and Nicola.
I didn't read the paper, so I don't know full detail, but
Sure.
they show any sort of convergence that you see in some certain regime. So if there's high temperature, here it's probably something different.
They're still exploring it. The main examples they show in the paper are quite nice. They mainly did AKLT wave functions. So they construct AKLT on various lattices like hexagonal and square. And they showed that it's converging exponentially fast, the free energy or the norm, those systems, which is probably one of the hardest quantities. So many other quantities we probably get much faster. They also tried certain random PEPs where you create bell pairs between all the sites at certain collections of bell pairs and then project them into the physical space and otherwise put random parameters in some of the projectors. And those also worked extremely well. They haven't tried, specific Hamiltonians other than the parent Hamiltonians for the AKLT. We'll see. Certainly there's cases that'll break it. Like you can imagine, you can encode all kind of, like 3-sat counting problems in the PEPs, that's not gonna work. So we know it's not going to violate any theorems, but it might work in a lot of physical cases. So pretty neat.
So it's working well in sort of gap theories.
Exactly. So it would be really nice to know, is gapless do you just get corrections? Like you just have to work a little bit harder, or does it just totally fail? How general, what are the general statements one can make? How general? That'd be interesting to know.
Is it something that substitutes DMRG? Should I think about it?
In a way, yeah, quite like that. Right now, it's more substituting slightly weaker variants of DMRG, like imaginary time evolution, which is a little slower way of getting to the ground state. DMRG is like a thing that just jumps to the ground state really fast. These are more technical differences. To do DMRG, we would just need a little more pieces mathematically. In order to run the kind of core algorithm of DMRG better. Basically, DMRG has this detail where you can solve a regular eigenvalue problem locally, Here we would have to solve a generalized eigenvalue problem. So it could become ill-conditioned. There's like little, it's a good question. There's technical steps that we have to think about. We're thinking about them though, yeah.
The beginning of the talk, I introduced how to map tensor networks into continuous variables. So I'm just, it might be a stupid question, but let's say if we have a state of a ground state. Let's say we have a 1D chain. And we prepare a ground state in a tensor network. And each point have like zeros or ones. So it is safely gone into zeros and one by continuous mapping.
Yeah.
So what happens if you just prepare any gap ground state and just change into your 1D function? How does the function look like?
Oh, like what if you just reinterpret
Yeah.
the sites as, yeah, it's a real good question.
And
I've even plotted some, I took some famous 1D states and I just plotted them on a grid as if the sites were continuous functions and they looked really wild. Like they just looked like these insane fractals or something. So, I mean, it's a real good question. I think right now, I think these are just kind of occupying slightly different parts of Hilbert space. I think the structures are rather different.
But my hope
Yeah.
is if you have a critical, so if you're not the gap state, ground state of the gap state, but if it's a ground state of critical space, so critical, you have like CFT. So if you map that critical state into your continuous function, it might have self-similarities. But I'm not sure if.
Yeah, I mean, I think you're asking something really interesting, and I think there's possibilities there. I think the possibilities, though, might be a little more fruitful in the direction of like thinking of these as representing individual degrees of freedom, like grouping the groups represent, like how I mentioned, you could represent a single rotor as a chain of bits. And I think that actually has, the reason I think it's maybe a little less connected for the like a whole many-body state is because the key point is that when you're representing these functions, the tensors are no longer working at kind of the same level, so to speak. Like by level, I mean, they're not at the same scale. So the ones in the subleading bits, they're not doing as much. They're like at a different scale. Whereas for spin chain, they're all occupying a bin of space that's equally important as the other ones. So it's just a very different usage. So you can almost, like one thing we've been doing is kind of trivial, but it's like we'll write the MPS that represent wave functions horizontally, and we'll write the ones that represent functions down the page. I mean, of course that's trivial, but the point is that we like to think of it as representing different scales. So you can kind of think of this one as representing a coarse scale, a finer scale, and then a much finer scale, So like as Juan said about wavelets, it's like, this is just putting on tiny corrections onto the function or handling very high frequency stuff that it's a bit optional. Like you could truncate that away and still do it. Whereas here, if you truncate away one of your spins in a spin chain, it's catastrophic, right? But here, these are kind of the bit optional at the end of the chain. So it's a very different usage of the tensors in that specific way.
So does that mean that like the tensor's translation, like if you have translation invariance in your state, then that would map onto like a scale invariance of some sort in your
Let's see.
function?
It's a good question. Yeah, I think maybe just the way I'll answer that would just be by giving you a formula, and then I think it'll be like homework for all of us, because I don't know if I have a smart answer, but I think I have some good test cases that I can give us all to think about. So the fun one is this. The fun one to think about is if you have e to the ax, and a could be generally a complex number if you want. And then how do you use it in this formalism? So what you do is you say b1 over 2 plus b2 over 4. This is the mapping written more, analytically. And then the reason this is a product state is just the usual sum of, exponential of a sum turns into a product. So you can write it as e to the a over to the b1. And here the b's are, bk is either 0 or 1. So it's that e to the a over 4, b2, e to the a over 2 to the n, bn. So then, I'll leave it to you to think about, like, if I translate what kind of happens inside of this machine. And also, this may answer your question a little bit too about, you see how this one is barely doing anything, because if A is like a real number, this is almost one. So this tensor is barely changing things. This one is very important. It's really quite different from like a ground state or something.
But if it had like an exponential correlation, it has a correlation length, so it has exponential decay. It doesn't have to go amplitude by decay as it go as you go finer and finer.
Yeah, the closest thing I can answer to that is that what a correlation function might be measuring would be something like how correlated you are in the scales. So you could imagine a function like this, so a very strange function, where what if you had a function that was very wiggly on the left half of the system, and as soon as you cross one half, it's really smooth. Then it's very highly correlated across scales, because what the first bit is doing, which is saying, are you on the left half or the right half, is very correlated with what the last bit is doing. But you would have to be something like that. So you could imagine if this is like a scattering, one of those 1D, quantum one scattering homework problems, that one might actually have a funny correlation across scales because of the existence of a scatterer or something. So that could be like the case that you're thinking about, But if the function was just smooth all the way across, the correlation is very local in the scales, because you just have to know, am I here or here, and should I be going up or down a little bit? But it's all very local. You don't have to really worry too globally. Am I the left half or the right half or something? Thanks.
Okay, there are no more questions. Let's thank Miles again.